Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. Hello, everyone. My name is Stefan Soroyo. I'm a researcher in the Mobility and Networking Research Group. It's my pleasure today to host Chen Chen, who is a graduate student from ETH Zurich. Chen was a summer internship with Alec and I last summer, and he's going to tell us about his work over the summer called cTPM. Now, the format of the talk is a little unique. It's, sort of we have two goals in mind. One is to present this work at MSR, but also to have a little bit of a practice talk for him. He's going to give this talk tomorrow at this conference in Seattle. So if you don't mind, if you can hold your questions until the end. So he's going to talk for about 20, 25 minutes. And after I will have ample time to discuss and ask all your questions, and we actually welcome all sorts of discussions afterwards. But that will give us a little bit of an opportunity to time his talk and have an idea. Anyway, so Chen is from ETH. Like I said, his advisor is Adrian Perig, who has recently moved from CMU to ETH, and Chen moved with him. Go ahead.
Thank you, Stefan. Hello, everyone. My name is Chen Chen from ETH Zurich. Today, I'm going to present my work, cTPM, a cloud TPM for cross-device trusted applications. This is joint work with Himanshu Raj, Stefan Sariu, and Alec Woolman from Microsoft Research. To motivate our work, today people are increasingly using more than one mobile device, and sharing data across these devices has greatly boosted user experiences. As another trend in mobile computing world, mobile trusted applications have started to use trusted hardware. One important such trusted hardware is TPM. And for example, Google Chromebooks use TPM for different features, including firmware rollback prevention and file encryption. And Windows 8 use TPM for applications like BitLocker and virtual smart cards. There are also many research prototypes proposed by the research community. Among them are Pasture, which offers secure offline data access, trusted sensors, which use TPM to send the sensor readings, and trusted language runtime, which provides a .NET language runtime for building trusted applications. We further notice that cross-device data sharing is easy. Today, in fact, most applications build some form of data sharing or app state sharing across multiple devices to boost user experiences. However, for these trusted applications, which usually stores their app state, data, or crypto keys in trusted hardware like TPM, sharing this TPM-protected data becomes hard. The primary reason for this difficulty is that the keys managed and protected by the TPMs are by TPM design bound to that TPM chip. Let me use these animations to show why this is the case. At the beginning, a set of root keys are installed in the TPM chip by manufacturers. And after that, these root keys are guaranteed never leave the TPM chip. And the keys created by the TPM will either be in the TPM chip or protected by these root keys when they are outside of the TPM chip. As a result, as long as these root keys never leave TPMs, this key generated by the TPM will be secret only to the TPM chip itself. Current TPM specification did provide a mechanism for key migration. However, to use this key migration, which is to migrate the key from one TPM to another, a PKI from a third party has to be provisioned. Also, configuration of this key migration has to run in a malware-free environment. Both of these requirements are actually challenging to mobile devices. I will come back to this point in 2 minutes. So the main research question in this work is, what is the minimum change we can make to the TPM design to enable cross-device data sharing? Our answer to that question is cTPM, which is short for Cloud TPM. As indicated by the name, cTPM uses cloud services to provide multiple features, including key migration across TPMs. Compared to the current TPM design, the primary change we made is to require additional root keys pre-shared with the cloud. Let me give you a flavor about how we can use these root keys to enable easy data sharing across TPMs. Let's assume two cTPMs running on two mobile devices and belonging to the same user. And the cloud provides two TPM emulators as cloud service for the user. And these two TPM emulators are bound to the same user. And each of the cTPM will share root keys with one of the TPM emulators. With the root keys shared between the cTPM and TPM emulators, we can then establish a secure communication channel between each pair of cTPM and TPM emulators. With this secure communication channel and with the help of the cloud, sharing TPM-protected data becomes easy. What's more, with the established secure channel, the cloud could further provide additional two features for cTPM. Today, TPM chip usually has a small and slow persistent storage device called NVRAM. Each slot in NVRAM could only be written around 10,000 times during its entire life. With the established secure channel, the first feature that the cloud can provide to cTPM is a fast and large remote NV storage. As for the second feature, current TPM chip only has a trusted timer in their design. It doesn't have a trusted clock. That means the policy this movie can only be watched after midnight Friday cannot be enabled. With this established secure channel, now the TPM can build a clock and sync this clock with the clock in the cloud. And now this helps enable multiple interesting time-relevant policies. Here's the outline of my today's talk. So after talking about our motivation, let's talk about the TPM as the background in case people are not familiar with it. And then I will talk about why design alternatives are not favorable. TPM is short for Trusted Platform Module. It is a secure coprocessor offering multiple crypto primitives. It also enables measurement and attestation of code running in the platform. It is vital for trust computing technology and is widely deployed in laptops by the producers such as HP or Dell or etc. And nowadays, Trust Computing Group defines specification for TPM. Current completed specification is TPM 1.2. It is widely deployed in the TPM chip available. And there's one additional specification to replace TPM 1.2, that is TPM 2.0. And our cTPM is based on TPM 2.0. But I want to point out that our design does not rely on any feature specific to TPM 2.0. Our cTPM can be easily applied to TPM 1.2. In this work, we adopt similar threat model to current TPM. That is, all sorts of software attacks, including malware, will be considered in our threat model. However, we don't consider hardware attacks, such as microscoping the TPM chip and read out the root keys. For the trust assumption, cTPM keeps a dual relationship with the cloud. On one hand, it trusted the cloud with all the shared root keys with the cloud, and the keys derived from these root keys. However, it isolates the root keys that exist in current TPM design and keep these keys local to the TPM chip. As a result, if the cloud is compromised, only the key shared with the cloud will be compromised. The keys that are local to TPM chip are still secure. Secure the cloud service without trusting the cloud has been an active research area. And we leave securing the cloud side of cTPM as our future work. For now, let's assume that the cloud can be trusted not to leak the shared root keys. As a design alternative, secure execution mode could be used to implement TPM extensibility mechanism. This mode is also called trust execution technology in Intel. It implements a CPU-based reboot and set up isolated environment to run trusted code. It could be generally used to implement additional TPM functionalities, such as key migration across TPMs. In order to remove operating system out of the trust computing base, we can implement additional TPM code in 2 steps. In the first step, we suspend the operating system and initiate this secure execution mode. And then, within this mode, we can run this additional TPM code. In the second step, after the code is finished, we can do necessary cleanup and exit secure execution mode and continue to resume operating system. These 2 steps may seem simple. However, it is quite challenging to use secure execution mode in this way. First, it poses some performance issues. As the operating system and all the applications has to be suspended in the platform, no progress can be made by the entire platform until this additional code for TPM is finished. And also, since the operating system doesn't exist in this secure execution mode, the additional TPM code is like running on a bare metal. Therefore, it causes some engineering issues for the developer of this additional TPM code. In fact, today, the ARM processor doesn't have this secure execution mode, which prevents the majority of this mobile device to use it from beginning. As a proof of these challenges, actually, there is no production software using secure execution mode in this way. After briefly talking about design alternatives, let's talk about our cTPM design and the implementations. In this section, we will mainly address 5 design challenges. First, what are these root keys, and how do we provision them? Second, with these root keys, how do we design easy secure key sharing across devices? And we will see that this requires a secure communication channel. And next, I will talk about the details of this secure communication channel. And finally, with this secure communication channel enabled, I will briefly talk about how we design cloud-backed NV storage and trusted cloud. First, for the additional pre-shared root keys with the cloud are cTPM's root of trust. cTPM generates these root keys using a random seed pre-share with the cloud. You can imagine that in the future, iPhone and iPad can share a random seed with iCloud. And Microsoft Surfaces can share a random seed with Microsoft Azure. And with this random seed on each boot up, cTPM can specifically generate 2 root keys. The first one is called Cloud Root Key, or CRK. It is used to protect all the secrets shared across TPMs and with the cloud. The second key is called Cloud Communication Key, or CCK. It is used to protect the data exchanged between cTPM and the cloud, and to establish this secure communication channel. So let's talk about our design of secure key sharing across cTPMs. The Cloud Root Key plays a significant role here. Suppose 2 cTPMs on 2 mobile devices belonging to the same user want to share keys. In cTPM, this is done in 3 steps. In the first step, the user asks the cloud to generate a shared key for its devices. The cloud will use command TPM-to-create to create a shared key among these 2 TPM emulators. And the shared key output by this TPM-to-create will be protected by the CRK of each TPM emulators. And in the next step, the key will be shipped with this secure communication channel to cTPM. And in the final step, the cTPM device can just use the command TPM-to-load to load the shared key protected by the CRK, and then obtain a handle for later use. So at a high level, the cTPM only executes one simple command, and it doesn't require either secure execution mode or PKI. The only missing component here is this secure communication channel in step 2. So let's talk about these details about this secure communication channel. In cTPM, we use cloud-side NVRAM as the message box for the cTPM device and the cloud to communicate. In general, sending and receiving messages by cTPM is like a NV-write and NV-read to the cloud-side NVRAM. You can think of this abstraction like the design in Unix, where the kernel code and the user mode code use the file system interfaces to communicate with each other. And also, as transient network connectivity loss is common on mobile devices, we further design a client-side cache to mask this transient network connectivity loss. And we provide synchronization protocols to sync the client-side cache with the cloud-side persistent storage device. Here are the details of our synchronization protocols. We design a pull and a push method for NV-read and NV-write. Each of the synchronization process includes two messages switched between cTPM and the cloud. Here I only want to highlight two details about our synchronization protocols. First, the messages are protected by the cloud communication key. Second, the counter and nonce are used to prevent message replace by the software stacks on mobile device and the network node in the middle between the cTPM and the cloud. I further want to point out that in each of the synchronization protocol, it is the TPM who initiates the connection with the cloud. However, in current TPM usage model, TPM is supposed to handle command and return result. It cannot initiate connection with the cloud. So there is a problem. To solve this problem, we propose a method called secure asynchronous communication. In this method, the caller app assumes the positions of a connection initiator and message forwarder. Each synchronization process will be divided into three phases. In the first phase, the caller app issues a command to cTPM and obtain a blob from cTPM. In the second phase, the caller app will forward this blob to the cloud and obtain a response blob prime from the cloud. In the third phase, the caller app will forward this blob prime to cTPM and obtain the result for the command. One observation of this method is, in phase 1 and phase 3, whose latency could be very short, cTPM will be blocking. It will not handle command from other caller application. However, in phase 2, whose latency is dominated by network latency, and this latency could potentially be very long, cTPM can continue to handle command from other caller apps. This helps to improve the responsiveness and availability of cTPM for other caller applications. And next, I want to remind you that here only cTPM and the cloud are trusted. The caller app is not trusted. So here, essentially, we create a secure communication channel based on the entities we do not trust. So with this secure communication channel established, let's talk about how we can design cloud-backed NV storage and trusted clock. Here is a picture to show how a remote NV RAM slot could be read. During this process, a synchronization protocol is used to sync the client-side cache with the cloud-side persistent storage. After that, the client can just use a NV read to read the content out of the local cache. Suppose the caller app would like to read NV index 42 from the cloud. It will first issue TPM-to-sync begin, which is a new command implemented by cTPM, to tell cTPM it wants to access NV42. In the second phase, the cloud could use TPM-to-sync proc to process the blob and return a response. In the third phase, the caller app can use TPM-to-sync end to let cTPM to process the response and obtain a return code of this command. If the return code is a success, that means synchronization protocol successfully sync the local TPM cache with the cloud-side persistent storage. Now, in the final phase, the caller app can issue NV read to read the content from this local cache. In our remote NV storage design, all the local cached NV entries will have TTL values. If the TTL expires, so the cached NV entry is no longer available. It has to be resynced. Also, cTPM has a timeout to abort these pending cloud commands. The cloud could adjust this timeout value according to its needs. The current default value is 5 minutes. Finally, with this remote NV storage established, building a trusted clock for cTPM is relatively straightforward. The cloud can just reserve a special NV index for the client, and put the clock information into this special index. Now the client can read the clock information out of this special NV index and even build policies upon this NV index. The only difference between this special NV index and other normal NV index is it uses a different timeout to keep high precision. The default value for this timeout is 1 second. For implementation details, in total, cTPM adds 3 new commands outside of 108 commands in current TPM 2.0 specification. And the usage of these commands are covered in previous slides. Our cTPM is implemented based on TPM 2.0 reference implementation. It involves 1,300 lines of code outside of 23,000. Finally, to prove the usefulness of cTPM, we re-implement Pasture and TrInc to work with cTPM. For Pasture, we extended its functionality to work across multiple devices. And for TrInc, we provide a high-performance NVRAM for it. After talking about our basic cTPM design and the implementation details, let me share some evaluation results. Our evaluation testbed uses a client-side machine equipped with TPM chip to run cTPM client-side code. We also set up a server running a TPM emulator in virtual machine for the cloud service. We use wide area network emulator to emulate both Wi-Fi and 3G network. We adopt the round-trip time information reported by Huang in Mobisys 2012. Specifically, in this section, we would like to answer 3 questions. First, are the cTPM protocol designed here secure? Second, what is the performance of crypto operations of cTPM? And finally, what is the performance of a remote NVRAM accesses for cTPM? To answer the first question, we verify the correctness of synchronization protocols with the verifier ProVerif. Here, we model attacker with unrestricted access to applications, operating systems, and the networks. And I want to point out that the verification is upon a model of our synchronization protocols. We didn't verify the correctness of our implementation. To answer the second question, we use an experiment to compare the crypto operation between cTPM and the TPM chip. In the experiment, we create a 2048 bits key on both TPM chip and the cTPM cloud-side emulator. And we compare the latency of each round of this key creation. In the figure shows in the bottom, the x-axis depicts the number of the rounds to create this key. And the y-axis shows the latency of each round. The result demonstrated here shows that the latency of cTPM to create a 2048 RSA key is 12 times smaller than that of a TPM chip. And the variation is much smaller. The primary reason for this difference is because the crypto operation and an entropy source on our cTPM software emulator are much faster than that of a TPM chip. And we expect this gap to be even larger when the cloud uses a faster entropy source and a better hardware crypto module to build TPM emulators. To answer the third question, we use experiment to compare the performance between remote NV access and the local NV access. We measure the latency of accessing an NV index of 640 bytes. As the remote NV access usually requires a three-phases synchronization protocol, we actually profile each step of the synchronization protocol. In the figure shows in the below, the x-axis shows the different operations on different network connections. And y-axis shows the latency of each operation. And different color shows the latency of different steps in remote NV accesses. The result demonstrates that for a remote NV read, its performance is comparable to that of a local NV read. However, for a remote NV write, its latency is 3.5 times smaller than that of a local NV write. And also, the latency of a remote NV accesses is actually dominated by the network latency. So we can expect with better locality in access pattern and batched operation optimization, this performance for remote NV accesses could be better. To summarize, in this work, we present cTPM, which is essentially a TPM chip with additional random seed shared with the cloud. We demonstrate that with this additional random seed shared with the cloud, we can enable cross-device scenarios. We can easily support cross-device scenarios by supporting cross-TPM data sharing. The design change also enables two additional features. They are high-performance NV storage and trusted clock. Finally, we present the full implementation of cTPM, and we also re-implement Pasture and TrInc and extend their functionalities with cTPM. So with that, I will end my today's talk. I would like to answer your questions. Thank you.
So now you're welcome to ask any questions you like. The harder, the better.
So what kind of applications are you targeting with this? I mean, you mentioned things like BitLocker at the beginning of the talk that just use the local TPM. And what new applications or what modifications of existing applications would
I see.
enable?
The question is, so what applications we enabled? Like, for example, can we, like, what additional functionality that we can provide for BitLocker? A good question. So the main applications considered in this work are like the research prototypes like Pasture and TrInc. So for Pasture previously, let me show you this. Oh, sorry. So the semantics of Pasture with cTPM may be complex, but let's compare Pasture, the traditional Pasture, and Pasture with cTPM. For this traditional unmodified Pasture, when it works on multiple devices, so we have to run Pasture protocol in a lockstep on multiple devices. For example, if Pasture is for, for example, to manage movies offline, okay? So when user buy movie from the cloud provider, and it use Pasture to say, I want to watch the movie, or I don't want to watch the movie. However, if with the traditional Pasture, when the movie if the user have two devices and has to, when it want to buy a new movie, it has to find all its mobile devices and make decisions about its previous movies. So with cTPM, Pasture with cTPM, so when the user has multiple movies, it can just continue to buy movies or choose watch or not watch on one device, and all the decisions can be synced to other devices with the cloud. But however, the difficulty here is to do all the things in a secure manner. So if you look at the Pasture semantics, so achieve this is actually hard without cTPM. Okay, and further for TrInc is used to solve equivocation problem for distributed system. So the key problem for TrInc is require a counter in NVRAM, which can potentially just be written around 10,000 times during its lifetime. And with cTPM enabled, so we can provide this high performance NVRAM for the chip, and therefore makes TrInc more accessible to mobile devices. So for the BitLocker, since I'm not very clear about its semantics with TPM, so I cannot reason about it now. But I would like to talk with you more about this cTPM and BitLocker to see how we can build a better BitLocker.
I think that answered. The other thing would be, so another benefit of this sort of for our platform would be that today if I have multiple laptops or multiple phones, I have to provision a virtual smart card separately on each of them. With this, it will be automatically sort of provisioned for me once I decide to do that across all my devices, because the cloud or the enterprise, if you want to imagine that, could know what is the right virtual smart card to generate for me and have it ready for me, so that when my device connects to the cloud next, already comes provisioned. And with BitLocker, one other benefit I think would be, although he's right in that we haven't thought through very carefully through the details, would be that you could imagine devices share the BitLocker encryption credentials, keys, and that might make some optimizations interesting, where you can bulk copy data from one hard drive to another, from one machine to another, and you don't have to decrypt and re-encrypt. It would be just sort of perfectly accessible.
And I don't have to remember as many.
And you don't, yeah.
So my favorite example would be to just have these mobile device password managers, just to have that so that it's automatically TPM protected and synchronized across all of my mobile devices. It's sort of the key motivator for me.
I mean, we have time for questions, but if that's it, that's fine too.
Well, you've got this slide up here. So when you're handling timeouts and the timers, do you have to do any writes to the local VRAM? Or is...
I see. So the question is, when we have this timeout, this TTL logic, do we have to access this local NVRAM to get it to work?
Yeah, in particular, do you have to do a write to
Yeah, so we don't. So because the TPM chip will have RAM built inside. So all this logic will be built in the RAM. So think about why we can build it in the RAM instead of NVRAM. If it is building in NVRAM, when the TPM crashes, the information stays. However, for these TTL values, it's when the TPM crashes or lose battery, then it doesn't matter if we can reset the TTL value, because it's just the lifetime for this local cache, and the local cache is already gone. so we don't have to store the TTL value. So, and also, this helps to make this local NVRAM have a longer lifetime.
Are there any scenarios where if you lost connectivity to the cloud for a long period of time, then you would be worse off by using cTPM?
Good question. So question is, what if we lost the connection with the cloud? What functionalities could be harmed by this loss of connectivity? So to answer the question, let's assume another scenario, which is Gmail. And if we want to use Gmail, and we lost our network connectivity, so we basically cannot send emails, right? And we probably can still see the emails in local cache, right? And if you look at cTPM as a cloud service, and then when the connectivity is lost, so it cannot communicate with the cloud for example, clock information or the content stored in the cloud. However, it can still read informations or write information to its local cache. And as long as this cache is not expired, because it's the TTL value, it can be used. But however, if this network connectivity is too long, this cache works only with transient network connectivity, right? So the cache will ultimately be expired. Then this cloud service cannot be used by cTPM.
So another sort of answer I would give at a high level is that the cloud made us more ambitious with the application, so we provide sort of new functionality. And we always make sure that functionality is secure in exchange. So for example, when you lose your network connectivity, there are cases when that extra functionality becomes unavailable. It stops working. And you could argue, I think you could argue in some cases that the way it stops work is in fact worse than having a pure TPM that would not offer this extra functionality, but might continue to make some sort of progress in the disconnected phase because you have the TPM locally. You see what I mean? So it's, in some sense, the way we're thinking about it is this: what the application developers should actually understand the usage model and say, well, I'm willing to actually take the risk of stopping this extra functionality and making the thing worse for the user just because I can offer this extra functionality. And in that case, they should use these tricks. Or it can say, you know what, I don't need this cloud thing. I don't want to deal with the loss. And in which case, you should fall back on the old TPM because we leave that there.
But you could design your apps in such a way that they have fallback paths so that whenever the cloud resources are unavailable, they have some fallback mechanism that just uses the TPM local resources.
But it's true that there are cases when being disconnected with the cloud will turn off all the cTPM functionality, all these cloud hierarchy. You won't be able to access it all because.
So you do want to think hard about what your timeout value should be relative to your expected network connection characteristics.
Okay. Okay. Thanks.
Thanks.
Thank you for coming.